So again, for the Henry's law, we also want to talk about the pressure-dependent composition plot. The x-axis is still your xb. You still have component A and B. You still have your PB star, PA star, assuming your B is actually more volatile. Okay, so if you have ideal solutions, then it's actually straight lines. But if today you have a non-ideal solution, then you won't actually see the straight line, okay? It's going to deviate from the straight line. That's why I call it non-ideal. So now the question I have for you is, under what conditions you are going to have ideal solutions? Let's say if today you have a very high concentration of B versus very low concentration of B, which condition is going to give you ideal solution? To answer this question properly, you need to actually think about what is the definition of ideal solution. What we say in the beginning is if you mix A and B, the interaction between AA, BB, AB, they are all similar, then we call it ideal solution, right? So for the non-ideal solution means actually your AB interaction is going to be very, very different from your AA or BB interaction. That means actually if you have a lot of AB, then it's going to become more non-ideal. So in this case, if you have very high concentration of B, then it actually looks more ideal. It looks more like ideal solution. If you have a low concentration of B, it is actually going to be look more like non-ideal, okay? But because at the same time, you actually have high concentration of A. So for B, it's going to be a non-ideal solution, but for A, it will be more or less ideal. Okay, so to answer this question, it's really like depending on where you stand. If you just look at B, then high concentration will be more like the ideal solution. And the low concentration will be the non-ideal solution. So here we know your PI is simply equals to your PI star times your XB. So that's how you handle the ideal solution, right? For your non-ideal solution, the PI is going to equals to your KH times your XB. This specific rule is actually so-called the Henry's law. Henry's law is actually the law that only apply to solutions where the component of your target is at very low concentration. And the KH is so-called the Henry's law's constant. Very high concentration area, it will behave more or less like ideal solution. All the things we learn from Rao's law can be applied to this region. If today you have a very low concentration of B, which is actually somewhere here, the solution is actually non-ideal because you're going to have a strong interaction between your A and B. But even though that's the situation, because the concentration of B is so low, it actually also sort of follow a linear behavior in the end. Henry's is actually the guy who actually discovered this. If you look at these two equations, they follow very similar form, right? Pressure is equals to the pressure of pure substance times more fractions for your ideal solution. The other one is actually the vapor pressure of your component I is equals to more fraction times a constant called Kh. Okay, so by now you should be very familiar with this plot. Right? The things you have right now on the plot is actually a very typical plot that you're going to see for the ideal solutions. We always draw these linear lines for the ideal solution, right? And then this will be actually the line you use to actually describe the P total of your solution. So if today you have non-ideal solution, how would it look like? Every time when I say non-ideal solution, that means you won't be able to see this linear relationship anymore. That means it's going to deviate from this ideal solution curve. If you plot out the vapor pressure of each individual component, let's look at B first. So previously we say that's actually the line you can have to describe the behavior of your B, right? If you are actually at high concentration, which is actually somewhere here, even though today you have a non-ideal solution, it will behave more or less like an ideal solution. If you plot out this pressure composition dependent plot at this region, it's going to be very close to the ideal solution line. If you keep decreasing the concentration, then it's going to start to deviate from the ideal solution line. In the end, you know, once you go to these regions, you'll look something like this. Key thing here is at high concentration, it's actually overlap pretty well with your ideal solution curve in the beginning. And then once you change in the concentration of a B, then you start to deviate from the ideal curve. And in the end, go back to this point. So let's look at this part. When your component B is actually very low in concentration, if you look at this area more carefully, you will realize that, yes, it deviates from your ideal situation. However, at least in this very tiny area, the vapor pressure is still actually linearly proportional to your mole fraction. So what it means is if today you can just use this curve, you can actually draw a line that eventually hit your y-axis. And the point that you have this intercept, we are going to call it as KBH. Okay, and that is actually the KH we are actually highlighting here. So what it tells us is that if I'm at a very low concentration for a non-ideal solution, I can still describe my vapor pressure of my component B using mole fraction. However, the prefactors right now is no longer to be your vapor pressure of B in a pure substance form. It actually goes into another reference state, KBH. Once you know your KBH, then you can always calculate the vapor pressure within this zone by using the Henry's law. Henry's law and Rouse's law, they look actually very, very similar. The difference between the two is that in Henry's law, you actually describe the non-ideal solution at very dilute condition. You are going to use your KBH to replace your PB star. So you can actually calculate the vapor pressure of B. For your ideal solution, that reference state will be your pure substance. For the non-ideal solution at dilute case, will be your Henry's law's constant. Basically, the Henry's law can actually help us to handle the non-ideal solution at diluted condition. In between, you cannot do anything. Henry's law did not actually handle the middle part. All right, so let's put these things again so you will see the things better. So for the ideal solution, we know you can calculate the vapor pressure of a substance I using your Pi star times the mole fraction of I, right? This equation is also true for the non-ideal solution when the concentration of your component is actually very high. But if today you have non-ideal solution at low concentration zone, then you know your Pi is going to equals to your KH times your Xi. So this is actually differences between the ideal solution and non-ideal solution at specific zones. From the ideal solution, there's actually another very important equation that we write is that we can actually write out the chemical potential mu I is going to equal to mu I star plus RT natural log Xi. And this is actually another very important equation that we always use to describe the chemical potential of components inside your ideal solution. So the next thing I want to say is what is actually the mu I for your non-ideal solutions at diluted case. To derive this, we actually start again from the concept of an equilibrium. Regardless you are ideal or non-ideal solution, when you are actually at equilibrium, the things you can always write is that at equilibrium, we know your mu in the liquid form is going to equal to your mu in the gas form. So how do we actually write out your mu g? So mu g is actually, again, we also write actually mu g naught plus RT natural log Pi, right? And then mu L will equals to your mu I. Okay, right now it's not pure substance anymore, okay? It's mu I H, okay? Plus RT natural log Xi. Okay, so your reference state is going to change. Okay, so your mu IH, okay, this can actually be written as your mu G naught plus RT natural log KIH. Okay, by combining all these things, you can rewrite your mu I is going to equals to mu G naught plus RT natural log KH XI. So this will be the final chemical potentials that you can use to describe the non-ideal solution at diluted case. Okay, so I guess I should put this here. So this should be actually mu I equals to mu G naught plus RT natural log KH times your XI. So you can actually compare the two. Basically, that's actually the most important two sets of equations. Let me highlight this. For your Rouse law and the Henry's law,